So in this video, we are going to do your coordination compounds, structure of coordination compound and how to find the magnetic behavior. So what will be the structure of coordination compounds and their magnetic behavior? Okay, with the help of your valence bond theory, we are going to do. So we are going to take some example molecules such as NiCl4. Number B, we are going to take your K4FeCN whole 6. Okay, then we are going to take all this and we will try to discuss how will be the shape and how will be your how will be the magnetic behavior of different compounds. Okay, so this has been done by in the help with the help of your valence bond theory. So these are five examples I'm taking. We can take more example if time permits. We are going to do that also. Yeah, so see this. First I'm doing number B. Why of your coordination compounds little bit. So see, coordination compounds is formed with the help of a metal atom, and it forms coordination bond with some non-metal atom, so that is called your ligand. So this is your ligand, okay, and this is your metal atom, central metal atom, okay, and this is also called your coordination number. The number of ligands also determine the coordination number. We will find the oxidation state of the central metal atom. Then we will go in detail. So see here, we know potassium is +1. Then here we know cyanide is minus 1. It takes up 1 electron easily. So this 6 -6, and here it is +1. So it should be how? +4. And here it says, so this is +2 state out here. Okay, so now iron, we know iron is Cr26. Okay, 26. So it's what is the electronic configuration? It is like this: argon 4s2 and your 3d6. Okay, so how Fe 2 plus 2 plus means it is like this one: argon 18, 3d6 only, because 2 electron has gone, so it is 2 plus. Now what we will draw, we will draw the hybridized orbital in this form. Like iron in ground state, sorry, in 2 plus state, what it is, what will it has. See, this is your d subshell. We will draw the energy level diagram. Okay, so this is your 3d, this is your 4s, and this is your 4p. Okay, now electrons now left 1, 2, 3, 4, 5, and 6. Okay, so now what is our compound? Our compound is your FeCN whole 6. So our compound contains cyanide atom. So cyanide ion is a strong field ligand. Strong field ligand. So whenever you have a strong field ligand, what it does, it forces the unpaired electron to pair up in a molecule. This is the difference between strong field and weak field ligand. Weak field ligand does not tell the electrons to pair up, whereas strong field ligand will force the electrons to pair up. Cyanide is your strong field ligand, and if I discuss about strong field and weak field ligand, then I will say weak field ligand are those ligands where the donor atom is your oxygen. Okay, the donor atom is your oxygen, or the donor atom is your bromine, your iodine, chlorine, fluorine. These are all your weak field ligands. Okay, where the either which is the donor atom is either oxygen, bromine, iodine, chlorine, fluorine, or sulfur. So these are all weak field ligands, and the strong field ligands are your those donor atom where there is carbon is or nitrogen is the donor atom, or phosphorus, carbon, nitrogen, and phosphorus. So carbon, nitrogen, and phosphorus, if they are donor, then it is a strong field ligand. And if for the weak field ligand, if oxygen is there and your halogens, okay, and your sulfur, so if these are the donor atom, then we say it will be a weak field ligand. Okay, so this is very important to note. Okay, and the most important we see in this weak field ligand, these are those molecules which will try to take up more electron, and these are bigger in size also. These iodine, bromine, chlorine, these are bigger in size, but fluorine is not a bigger in size, but it will try to take up electron so it to from the system and to finish it octet. So it does not want to give electrons. So those one which is a very good donor atom, okay, so that is called your strong field ligands. Even oxygen also, it will try to take up 2 electrons. It is always -2. It does not want to give. So but whereas in case of your strong field ligand, where carbon is there, carbon is there, then ammonia is there, nitrogen is there. So these are all giver. These are donor. Carbon monoxide is there. So these these molecules, they want to give the electron, where there is carbon is the donor, or nitrogen easily will try to give the electron, because by giving only it becomes octet. Okay, so these, when they form the coordination, they will go for your strong field ligand, and they will try the other pairs also to pair up, whereas these weak field ligand, they will not tell the other electrons to pair up. Okay, so this is the difference. So here iron in oxygen's excited state, what it will be, it will form it is cyanide, so it will pair up how many, 1 2 3 4 5 6, so it will be 5 6. Okay, so how many remaining in d orbitals, there is how many cyanide atom, 6. Okay, 1 2 3 4 5 6, so 4s and 4p. So it is forming what, it is forming D2sp3. So it is forming D2sp3 hybridization. So here your FeCN whole 6, it is, the shape is your octahedral, okay, because it is your D2sp3 hybridization. Okay, and there is no unpaired electrons, hence it is diamagnetic in behavior. Okay, and thirdly, what we can say, it is this is your inner orbital complex. Inner orbital complex. Why inner orbital? Because it is taking n-1, that is your d subshell. It is also using this d subshell for forming the hybridization, inner d, so it is inner orbital complex. Okay, so this way we will do all the other molecules also. Whole for 2 minus, so if it is 2 minus, the charge is 2 minus, so what will be nickel, it will be plus 2. Why? 4 minus 2, it is plus 2. Okay, so now nickel, we know nickel is, again we know it is 28, so it is argon 18, 3d 4s2 and 3d 8. Okay, so now let me draw the ground state structure of Ni2 plus. So what will it be if I do the hybridization, if I draw the subshells? Okay, so this is your 3d, 4s and 4p. How many electrons? 8 electrons. So 1 2 3 4 5 6 7 and your 8. Done. Now we know this chlorine, now it is a weak field ligand, weak field. Okay, so it will not try tell these electrons to pair up. So what will be now, nickel in the excited state? So what will it be? It will be like this. See, draw the subshell. So how many chlorine? 4 chlorine. So it will not pair up. It will remain like this only. Okay. Now chlorine atom. So what will happen to the chlorine atom? The chlorine atom now will come here. The chlorine atom is coming out here, 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 and here. Okay. And so how many? This is your 4s. This is your 4p orbitals, right? So it is forming what? It is forming your sp3. Okay, so what is the shape? Now, shape is your tetrahedral. We know why? Because it is sp3. sp3, so it is tetrahedral in shape, and it is, what is the magnetic behavior? It is diamagnetic or para? It is paramagnetic. Because it has 2 unpaired electrons. So we have done for nickel also. We'll go to the other example. Now see, now I'm doing with the Fe F6 3 minus. Okay, so again find the oxidation state. Oxidation state, here it is -1 for fluorine, so it is +3, because here it charge is -3, so it is +3. So iron, we know it is 26, so iron 2 plus, if I directly do, so what it will be, argon 3d, how much, 3d6. So draw this ground state 4s and 4p. This is your 3D 4s 4p. So 1 2 3 4 5 and 6. Okay, now see what it is. It is F6. F6 means weak field ligand. Fluorine, I told you, it is weak field ligand. So what are we going to do? So this will not tell that these electrons to pair up. So fluorine will come out here, fluorine will come out here, fluorine will come out here, and it is taking also, if it is 6, that means it is taking another, there is a d orbital. Okay, so this is 4d orbital. So how many it has taken? 1 2 3 4 5 and 6. So it is your sp3d2. So what it is, shape will be octahedral, octahedral. This is outer orbital complex, outer d, because it is using the outer d, so it is outer orbital complex. Okay, and the most importantly, it is magnetic behavior. It is diamagnetic or para. Okay, or it, we can also tell it to be ferromagnetic, because there are four number of unpaired electrons, so it can also act as very good magnetic compound also. Okay, so this can also be termed as ferro complexes. That is your cobalt NH3 whole 6 2 plus. This is we are going to do now. See ammonia, it is 0. Okay, so here it is 2 plus, so this will be plus 2 only. Okay, because this is 0, so total charge is plus 2, so it should be plus 2. Now cobalt, so cobalt is 27. If it is 27, then it is argon 18, 2 plus, it will be 3d7. Okay, so cobalt in your ground state, well, if what we were going to draw, how many electrons? 1 2 3 4 5 6 and 7 electrons. Okay, so this is your 3d, this is your 4s, and this is your 4p. Now cobalt in your excited state of 2 plus. Now say what is the thing here, the donor is your nitrogen, so it is a very strong, you can say donor, it is a strong field ligand. Okay, so it will, what it will do, it will now tell the electrons to pair up. It will tell the other electrons to pair up. So how many total electrons? 7. So 1 2 3 4 5 6 and 7, only one electron left. Now what will happen, there is 4d also, we know. Okay, so this is your 4d orbitals. So what happens, this one electron, okay, it will shift out here in 4d orbitals. Okay, so what is ammonia going to do, this NH3 will come out here, NH3 will come out here, because how many NH3? 6, 4 5 and 6 NH3. So this electron will shift here and it will be forming here. So now there will be only lone pair of ammonia out here. Okay, so because it is a strong field ligand, so what it is forming, now see, it is forming your D2 sp sp3. So it is your octahedral complex, and it is your diamagnetic in nature. Because it is taking two orbitals which is of inner d, so it is your inner orbital complex. So mostly this cobalt, we know it is cobalt 2 plus, cobalt 3 plus is more, cobalt 3 plus is more, you can say more stable. by experimental analysis we see that, because one electron, if it goes away, then it becomes 3 plus, so that is more stable. Now we will go for another example, and that will be the last example today. So that is your copper, NH3 whole 4 2 plus. Okay, so ammonia is 0, again plus 2. So copper excited state, it is your sorry, 4 is 2 copper, and copper 2 plus is your 3d9, so it is 9 electrons out here. So copper in your excited state, it will be 3d9, right? So 1 2 there are 9 electrons out here. In excited state, what will happen now? Because ammonia is again strong field ligand, nitrogen is, ammonia is a strong field ligand, so what will do, it will try all electrons of the subshell D should be paired. So what will it do, it will tell all these things to pair the unpaired electron, it will shift to 4p orbitals. And how many ammonia molecule are there? 4. So it is going to form like this, it is going to form your dsp2 hybridization. Okay, so it is forming dsp2 hybridization, and the shape is your square planar. Shape of dsp2 is your square planar, and it is paramagnetic or diamagnetic, it is diamagnetic. And also see here, this copper NH3 whole 4 2 plus, it is not oxidized, not oxidized to Cu NH3 whole 4 3 plus, like this. To remove this electron, if I remove this electron, but this copper does not ever form 3 plus. Why? And 3 plus, it will never form. Okay, so this is a demerit which cannot be explained by your valence bond theory. So it was the demerits of valence bond theory, because this does not exist. Okay, so we have discussed how to find the magnetic behavior, the shape and everything. So if you have some questions, then we will solve it in the other class. Thank you so much.